Hey there. So now we're going to talk about 4.2, which is going to be talking about the different types of studies we can be doing. Okay, so I'm just going to go through the PowerPoint and also remind you guys what's going to be on your notes, like what little blanks you need to fill in. Okay, so the first kind of study we're going to talk about are observational studies. Okay, basically these are things that you're only observing. You are not going to be changing anything in the study. So we have observational studies that happened in the past, okay? They examine existing data, so things that already happened. That is called retrospective. So this would be one blank you guys have to fill in. Okay, retrospective is that first blank in your notes. So those are observational studies that happened in the past. Okay, already happened. Observational studies that track individuals into the future, so you're following somebody along, that's called prospective. That's called a prospective study. So this is when they do those studies about, kids as they grow and how, something might affect their reading skills, from first grade to second grade to third grade. So as you're watching things happen, that is called prospective. Okay. Happens in the future. Okay. So again, I mentioned this before, observational studies, you observe individuals, but you do not try to change anything about them. You do not attempt to influence any of the responses. You're just watching. You are just observing. Okay. And we have the same stuff as before. Response variable will be, what's coming out of the study. And you're hoping the explanatory variable explains what happened in the response variable. Okay, so just like those scatter plots that we had, observational studies do not show causation. Observational studies just show that there might be a correlation. You don't know if something causes the other. So we're going to follow this example about vitamin D. Is taking vitamin D supplement good for you? Hundreds of observational studies have looked at the relationship between vitamin D concentration in a person's blood and various health outcomes. Okay, so with an observational study, we can't say vitamin D causes anything, okay? If it causes lower chance of diabetes, for example. All right, so we have the variable that we're looking at, vitamin D, but we also have these other like little variables, or just variables we're not looking at per se. Okay, quality of diet, amount of exercise, if they take a different vitamin supplement. Okay, we have one group of people who they take a lot of vitamin D, so they're less likely to have diabetes. So we're like, cool, vitamin D, less diabetes. Group 2, low vitamin D, more likely to have diabetes. Okay, so first you think, cool, more vitamin D, less likely to have diabetes. That's it. More vitamin D causes you to be less likely to have diabetes. However, there's these other variables, right? Like the fact that they have a better diet, they do more exercise, they take more vitamins. Those other variables that we're not really looking at are called confounding variables. Okay? Those are variables that might be influencing our response, and we don't want that. We want something to be very clear cut. Okay, so since we don't know if it's the vitamin D causing people to be less likely to have diabetes, or maybe it's their diet or their exercise, or they're more likely to take other vitamins, since we don't know which one it is causing the likelihood of diabetes to be reduced, that's confounding and we don't want it. So on your notes, I put possible confounding variables. It's these. So possible confounding variables. That would be the diet. That would be the other vitamins they take. And that would be their exercise level. All right, now, if we wanted to actually see if vitamin D causes a reduce in diabetes, we would have to do an experiment. Okay, that's the only way to show causation, is to do an experiment. So an experiment deliberately imposes a treatment. Like, we are purposefully saying, okay, you're going to do this and you're going to do this to hopefully reduce that confounding, okay, and to try to see if we can get a causation. So researchers in Norway performed an experiment about vitamin D. The researchers randomly assigned 500 people with pre-diabetes to either take a high dose of vitamin D or to take a placebo, a pill that looks exactly like vitamin D supplement but contained no active ingredient. After 5 years, about 40% of the people in each group were diagnosed with diabetes. Okay, so again, this is an experiment because I went and I got 500 people. Half got the vitamin D supplement, half got nothing. Or, they got a placebo. And a placebo is just a treatment that has no active ingredient. So I think a lot of you know what a placebo is. Okay, it's just like a fake pill, as it were. All right, so for us to see whether or not this experiment, caused whatever, take a look at what they said. 40% of people in each group. So they responded the same to the vitamin D as they did to the placebo. So we probably can't say vitamin D causes people to have a less likely chance of getting diabetes. Okay, so an experiment is a statistical study in which we actually do something, right? We impose a treatment to people, animals, or objects, okay? So a specific condition applied to the individuals. The thing we are giving people, whether it's a drug, whether it's a vitamin, whether it is a different colored shirt to wear, whatever the experiment is, the thing we're giving the people or the things are called treatments. So that's one of the things you guys have to fill in. Okay, it's called a treatment. The things we impose on our subjects. All right, if we have different explanatory variables, all right, so let's say I wonder if, wearing a certain color makes people nicer to you or something. Okay, the treatments would be wearing the blue shirt versus the red shirt versus the black shirt versus the white shirt. If my experiment was about shirts and pants, then it would be, the blue shirt with khaki pants and the blue shirt with jeans and the red shirt with khaki pants and the red shirt with jeans. Each combination would be a different treatment. Okay, so whatever it is you're giving people or making people do, each individual different thing is called the treatment. All right, an experimental unit is the object to which the treatment is assigned. So like each person that is wearing a different outfit, okay, that I'm making them wear different clothes, that would be an experimental unit. If it's a person, we usually call them subjects. Okay, we don't call people experimental units. It just sounds kind of mean. So we call them subjects if it's people. But if I'm doing an experiment on plants and I want to know if different amounts of fertilizer will have an effect on the plant, okay, or different amounts of water will have an effect on the plant would be the experimental unit. And the different amounts of fertilizer or the different amounts of water would be the treatment. All right. Malaria causes hundreds of thousands of deaths each year, with many of the victims being children. Will regular screening children for the malaria parasite and treating those who test positive reduce the proportion of children who develop the disease? Researchers worked with children in 101 schools in Kenya, randomly assigning half of the schools to receive regular screenings and follow-up treatments, and the remaining schools to receive no regular screening. Children at all 101 schools were tested for malaria at the end of the study. Identify the treatments and the experimental units in the study. Okay, so I think one of the easier things is the treatments. Who's getting what? Okay, what are the things that are being given to the people? So we're giving half of the schools are receiving regular screenings and follow-ups. So this would be one of the treatments. All right, so treatments would be regular screenings and follow-up treatments. Okay, and the other treatment would be no regular screening. So getting nothing is also a treatment. Okay, now the experimental units. What or who is getting the screenings or no screenings? Now you might think, oh, the kids are doing that. Nope. Look at how they worded it. They say they're randomly assigning half of the schools. So technically your experimental units are the schools. Yes, I get it that the kids are the ones getting the treatments or getting the screenings, but the way that things were assigned, they were assigned to the schools. Okay, so the experimental units are technically the schools. Technically it's the 101 schools in Kenya. Okay, so experimental units, again, are the things that are getting your treatments. In this case, it is going to be the schools. Half the schools got, regular screenings and follow-up. Half of them got nothing. Ta-da. All right. So, different example. Researchers from Rutgers University put the 5-second rule to the test. They used 4 different types of food: watermelon, bread and butter, and gummy candy. They dropped the food onto 4 different surfaces: stainless steel, ceramic tile, wood, and carpet. And they waited for 4 different lengths of time: less than 1 second, 5 seconds, 30 seconds, 300 seconds. Finally, they used a bacteria prepared 2 different ways in a tryptic soy broth or peptone buffer. Once the bacteria were ready, researchers spread them out on different surfaces and started dropping food. All right, so factors are the things we're changing. How many ways we change them are called the levels. Okay, so what are the factors here? What are the different things we're changing? We are changing the types of food. Okay, we are changing the surfaces. We are changing the lengths of time. And we are changing the way they prepared the bacteria. So we are going to have 4 different factors. Okay, the first one will be type of food, then surfaces, lengths of time, bacteria prep. Now, how many levels of each? I have 1, 2, 3, 4 levels for food. I have, let's use like a different, okay. I have 4 different levels for surfaces. I have 4 different levels for time: 1 second, 5, 30, 300. So I have 4 different levels for that. And then for the bacteria prep, we only got 2. We got this soy broth and this peptone buffer. Okay, so we have 4 things we're changing, so 4 factors, and each one has a different amount of levels. Food has 4 levels, surfaces has 4 levels, time has 4 levels, bacteria prep has 2. Okay, and again, that's because for food, we have 1, 2, bread with butter 3, and gummy candy 4. For surfaces, we have again 1, 2, 3, 4. For lengths of time, 1, 2, 3, 4 of them. And last but not least, bacteria prep, there was only 2, soy broth, peptone buffer. Okay, so again, factor, what we're changing, level, how many of those there are. Like how many of each factor there are. Okay, so we have, when we want to design our experiment, okay, this right here, have our experimental units, give them the treatment, and measure their response. This would be a bad experimental design. Okay, so this is bad. Why is this bad? Because I give them, let's say this treatment is the vitamin D. I give everybody vitamin D and see how they do. That's great and all, but I have all those other confounding variables, like their diet, like their exercise, like what other things are taking. Okay, so I need to be able to compare it with another group. It could be a control group, like the people who they could get no vitamin D, they can get the placebo, like pretend they're getting vitamin D, okay? Or they could be getting something else. Let's compare vitamin D with vitamin B12 or something, okay? So in your notes, it said, why is this bad? Okay, there's potentially confounding variables. Okay, so we have potentially confounding variables. And how we fix it, we do a comparative experiment with 2 or more groups. If you want, you can say like example, a control group. I know you guys have been doing science for a hot minute, so you probably are used to the phrase control group. All right, now to be more specific though, in your notes, I then said that in an experiment, a control group is used to provide a baseline to compare the effects of other treatments. So a control group may be given a placebo, so they might be given an inactive treatment like a placebo. They might get another treatment, like a different treatment, or no treatment at all. So I'll give you an example. We just did one about placebos. So you get vitamin D or you get a fake vitamin D pill placebo. When 2 groups might get both active treatments is, for example, a cancer study where, group A gets the existing cancer treatment and group B gets the new experimental cancer treatment. I'm not going to give one group of cancer patients no medication, like no chemo or no whatever. Like that's kind of messed up to give them no help with their cancer. Okay, so the second comparative group would be the group that gets the pre-existing cancer treatment. That way I can compare the new one to how the old treatment worked. All right, and then no treatment at all. Again, you could just see if, I have a group of 4th graders, and one group is going to be in a class where the teacher has, whatever reward system set up, and the other group has the same teacher, for the second half of the day, but she does not use the same reward system, right? So one group gets the treatment of the reward system, one group does not get the treatment. So you can get a placebo, a different treatment, you already know how they're going to respond to it, or they can get no treatment at all. So control group does not need to be no treatment. It just needs to be something you already know or you expect how they're going to react to it, so you can compare it to the treatment you're actually studying. Okay. Other than that, though, in every other respect, the treatments should be exactly the same so that the groups should be exactly the same so that the only difference is the treatment. That way, if there is a difference, you can make the conclusion it was caused by the thing you changed, by the treatment. Okay? If my cancer study, the people are responding super well to the new drug, okay? If everything else, if the groups are the same, the severity of their cancer is the same, both groups have the same amount of males versus females, everything you can think of is the same. The only difference is the treatments they were given, then I could say fairly confidently that whatever I see, whatever differences I see must have been caused by the treatments. Okay? Okay, that's what I just said. Cool. All right, so we also have a thing called the placebo effect. All right. It describes the fact that some subjects will, and you got to fill this out, just basically respond favorably to any treatment, even if it's inactive, even if it's a placebo. So you'll see this a lot with, for example, like let's say there was like a headache medication, okay? And I give some people the real, the real Excedrin, and I give some people just a placebo. If they respond favorably to the placebo, then I know that I can't conclude that my drug really worked because they responded favorably to the other thing too. So placebo effect just means they responded even to the fake treatment. Double blind. So this one's usually, a lot of studies like to be double blind. This is when basically nobody knows what's going on. Okay, neither the subjects nor those who interact with them and measure the response variable know which treatment is being received. Okay, so nobody knows who's getting what treatment. Somebody in an office somewhere knows that patient A or patient number 1 got treatment A and patient number 2 got treatment B, etc. But let's say it was the cancer study again, patient 1 has no idea what drug they're getting. Patient 2, no idea what drug they're getting. Even the nurses, all they know is patient 1 gets this bag. They don't know what the bag has in it. Let's say it's like IV fluid or whatever. And patient 2 gets this bag of IV fluid or whatever. They don't know what's in each bag. They just know this goes to this person, that goes to that person. So double blind. The subjects don't know what they're getting, and the people administering the treatment don't know what they're giving them. The only people who know is somebody in an office somewhere who wrote it down on paper. Okay, so double blind, nobody knows really who's getting what. Single blind is you can kind of like fill in the blanks here. It's just one half of the group knows who's getting what. It usually is that the subjects don't know, but the person administering the treatment knows. Sometimes it could be, it's really rare, but sometimes it could be that the subjects know what they're doing and what they're getting, but the people recording the information don't know. All right? So an example of that would be if I wanted to know how different forms of exercise affect, people's cholesterol levels. Obviously, the subjects have to know what type of exercise they're doing. Okay? And again, someone somewhere in an office assigned everybody to their type of treatment, to their type of exercise. But me as a person, recording the information and seeing how their cholesterol levels are going, I don't know who got what. All I know is here's subject number 1, I take a blood sample, I get their cholesterol level. Here's subject number 2, I take a blood sample, I get their cholesterol level. So me as the person collecting the data, I have no idea who did what. But the people doing the experiment, obviously they had to know what type of exercise to do. So sometimes that does happen where when it's single blind, the person collecting data doesn't know what's happening, but the people in the experiment do. Usually it's the other way around. Usually the people in the experiment don't know, but the person doing the data does. All right, so just like with random sampling, right? For sampling, we love random sampling. It's the best thing. So same thing with experiments, random assignment. We love it when we assign the treatments randomly. Okay, that helps us create roughly equivalent groups. Okay, hopefully I get roughly the same amount of men and women in each group. Hopefully I get the same amount of each ethnicity in each group. Okay, we use it to make roughly equivalent groups. So in your notes, I want you guys to, in your notes, I want you guys to make sure you write down random assignment means experimental units are assigned to treatments using chance. Okay, maybe we use the random int function on our calculators. Maybe we use, maybe we use like names in a hat or something. Okay, but people or the subjects are assigned to each treatment randomly. That is the main part. All right, so for example, a total of 20 students have agreed to participate in an experiment comparing the effects of caffeinated cola and caffeine-free cola on pulse rates. Describe how you would randomly assign 10 students to each of the two treatments using A, 20 identical slips of paper, technology, or table D. So, if we're using 20 identical slips of paper, okay, you could just write everybody's name on their own individual piece of paper, put them in a hat, randomly pick 10 pieces of paper. Those students would be in the caffeine group. The rest would be in caffeine-free. Okay, you could even do something like just write the words caffeine on 10 papers and caffeine-free on 10 papers and have the 20 people come in and pick a name or pick one of the papers randomly. Whoever got caffeine-free is in the caffeine-free group. Whoever got caffeine is in the caffeine group. Basically, something along those lines, okay? Your book technically wrote, write the letter A on 10 slips, and on the remaining 10, you write B. Shuffle them around, have each volunteer pick one. Those who got A receive the cola with caffeine, and those who got B receive caffeine-free. Okay, so you can totally do basically names in a hat to get your random assignment. For technology, it's the same thing I mentioned in 4.1. You have 3 steps. You're going to have to, 1, assign each person a number. So label each student with a different integer from 1 to 20. Then you have your calculator or whatever randomly generate 10 different unique integers from 1 to 20. Okay. And then last but not least, the people who go with those names, the people who correspond to those numbers are going to be in one group, in this case caffeine, and the rest of the people will be without caffeine. So when you're describing how you would randomly assign, you 1, label each person with a different number, assign a number to each person. 2, have your technology randomly generate 10 unique or different integers from 1 to 20. And then 3, those corresponding people with those numbers are going to be in one group, in this case caffeine. The rest will be in the other group without caffeine. Table D, that should be almost the same steps, except your table will help you randomly generate those numbers. So again, look, step 1, label each student with a different integer, assign a number to every person. If you remember, so you see how 20 has 2 digits, make sure the first number, so it should be also 2 digits, so 0, 1, okay? Because when you go to table D, remember, you're going to be going 2 digits, in this case, 2 digits at a time. So step 2, have your table D, okay? Go to line in table D and read 2-digit groups moving from left to right. The first 10 different labels between 1 and 20, identify the first 10 people who receive caffeine, and the rest of the people, you don't even have to keep going, the rest of the 10 people will get the caffeine-free group. Okay? So this right here, by the way, when it says ignore the groups of digits from 21 to 00, that's kind of like what we did in the hotels example, right? We had up to 28 hotels, so we ignored, numbers 84 and 40 and 92 or whatever numbers we had. You ignore the numbers that are not within your data. So we only had from 1 to 20. So everything else, we just ignored those numbers. But again, it's the same steps as technology. Assign everybody a number. Okay. Have your table identify 10 unique numbers. Okay. And those 10 will get one group. The remaining 10, I guess this will be number 3. The remaining 10 will get the other group. All right. So in an experiment, control means keeping everything the same for all the experimental units, right? Like, so your control group, everything is the same except for the treatment you give them. Okay. So any difference you see must be due to the treatment, right? Because everything else is kept the same. All right. Here you have the next blank in your notes. Replication in stats in an experiment does not mean doing the experiment over and over again. That's what it sounds like. However, what it means is using enough experimental units to distinguish between the effects of the treatment and just by chance. Okay, so instead of me doing the experiment 100 times, I'm just going to do it with 100 subjects. Does that make sense? Okay, so I'm not going to do my experiment over and over and over again. I'm just going to make sure I have enough subjects in my experiment to validate my conclusions. So, that's what basically it says. Replication means use enough subjects. So a study with just 5 people, not terribly, I feel like it's not very strong, but if an experiment with like 1,000 people, a little stronger. An experiment with like 10,000 people, a bit stronger. Okay. All right, so just putting it all together, we need to make sure that our experiments have something to compare. All right, we're comparing 2 or more treatments to see if one of them is going to have an effect on our desired result. We want to make sure that we randomly assign our treatments, okay, to make sure that our groups, our active treatment versus our inactive treatment, our placebo, or whatever, no treatment. We want to randomly assign to make sure those 2 groups are about the same in terms of whatever other variable there might be, diet, exercise, race, gender, whatever. We want to make sure that we control everything else, okay? We want to make sure almost everything for all groups is the same except for that treatment, okay? And again, replication, just making sure we have enough experimental units in each group so that basically whatever we find can't be just, we had a bad sample, or we had a bad, we only had 3 people, so maybe those 3 people are responding a certain way. No, we got to have a bunch of people to make sure, all right, whatever I found must be because of my treatment. All right, so you should have a second piece of paper for the 4.2 notes, okay? This is just a nice little diagram to show you guys how the completely randomized design should kind of look. First, we get our subjects, right? So this could be our experimental units. If it's people, we call them subjects. okay? Then we randomly assign them to the two groups. So let's say this is that vitamin D and diabetes thing again, right? So we give one group, so we randomly assign them to group 1, okay? And we give them the vitamin D. And the people who got randomly assigned to group 2, we're going to give them the placebo. And then after they, whatever the course of time was for that experiment, at the end, we compare the response variable. We compare it whether or not they did in fact develop diabetes to see if the treatment made any difference. Okay, so again, start with the people or the things in the experiment. Then we're going to split them into two groups using random assignments. We're going to give them the different treatments. And then once the experiment's over, we compare to see did the treatment have anything to do with anything. So, last but not least, there is a thing called block design. So you guys, well, I guess there's two things left. Well, so block design, it's kind of similar. If you want to make a little note for block design is kind of similar to that stratified stratified random sample, in the sense that I think that when I do my experiment, there's going to be groups in my experiment who are going to respond differently. Okay? So when that happens, I'm going to have to split my experimental units into groups first, and then basically do my experiment twice, with this group because I think they're going to respond one way, and then with the other group because I think they're going to respond another way. So, for example, there are some, pharmaceuticals out there that respond differently based on, gender or based on race. So if I think that's going to be an issue, let's say it's, it responds differently in guys versus girls. So what I would do is I have my experimental units, they're ready for the study. I would separate the men from the women, and then within the men, randomly assign them the new treatment versus the control, and then randomly assign the women new treatment versus control. Okay? That way, if there's a difference between how men respond and women respond, I have the data separate already, so I can see what's the difference it had within men, what's the difference it had within women, and then what's the difference it had in general. Okay? So if the blocks are chosen well, if they're formed wisely, it's easier. It's more obvious that you have evidence that one treatment was more effective than the other. Okay, so here's an example. So we have 10 volunteers, and I want to test these keyboards, right? So we have keyboard A, versus keyboard B. Okay, but what if, this book must be old because it says smartphone versus not smartphone. Okay, but let's say this is Android versus Apple, right? So if I think being on an Android is going to be different than being on an Apple phone, I might separate the users this way, then do that same thing I did before. Then I would randomly assign my Android users, some to keyboard A, some to keyboard B, compare how Android people did. Okay, I would do the same thing for Apple phone users, randomly assign them half to keyboard A, half to keyboard B, compare how Apple people did between the two keyboards, and then compare how everybody did between the two keyboards. So I don't know if you guys noticed this, but it is almost like having like this was one experiment almost, and then this was like a second experiment. So I split my experimental units, my subjects, into two groups. I split my experimental subjects into two groups first, or however many groups I need, run the experiment basically twice, and then after all of that, then I bring all my data together. So that's what randomized block design is. You split the data or the people or the whatever into groups first, then you run the experiment however many times. Okay, there's this last one called matched pairs. It's kind of like block design, except your blocks are just size 2. Very commonly, matched pairs, you'll see it, what I mean by blocks of size 2 is you'll see it with identical twins. Okay, one person gets treatment A, one person gets treatment B. So that's what I mean by blocks of size 2. Each group just has 2 people in it. I have one group of twins. I have one person get treatment A, one person get treatment B. Okay. Another way you might see this is you get the same person and they do the treatments twice. So if I want to know if the color shirt you wear affects how people respond to you, I'll be like, I'll have each person wear a blue shirt, go out and see, submit a survey saying how people responded to them in that colored shirt. I'd then have them come back, change the color of their shirt, go back out. So the same person does the next treatment as well. Okay, but this is what I mean, blocks of size 2, is I have one pair of twins doing both treatments. Right, so 1, 2. I have one person doing both treatments, 1, 2. We'll talk about that more in like a future chapter, but that's another type as well. All right. The main thing about matched pairs is just, again, like identical twins. They're pretty much the same person. They're as close to the same person as you can get without being the same person. So hopefully everything is controlled, right? Like they're both the same height, they're both the same weight, they're both the same gender, they're both the same DNA. The only thing different would be the treatments. The same person doing both treatments. They are literally the same person doing and the only difference would be the 2 treatments. Okay, so that's the main idea behind matched pairs. All right, so that's it for 4.2. Hope this video wasn't too long and too boring for you guys. Again, I'm going to remind you guys, please make sure you're checking Schoology for the problems that I'm going to assign for you guys. And when I come back, I will go over 4.1 and 4.2 and make sure if there's any lingering questions, I will go over that on the day I see you next. Okay? Have a wonderful time. Bye, guys.